Engineers spend enormous energy debating GPT-4 versus Claude versus Gemini, benchmarking token speeds and pricing tiers. But the dirty secret of production AI systems is this: when your agent breaks, the model is almost never the reason. The real culprit is almost always invisible. It's how you designed, stored, and retrieved state. By design, language models are stateless. Each API call is a blank slate. The model has zero memory of what happened a second ago, a minute ago, or last Tuesday. This is actually intentional for scalability and safety reasons. The problem is that the real-world tasks we assign these models, managing users, running workflows, executing multi-step reasoning, are deeply fundamentally stateful problems. To bridge the gap between stateless models and stateful problems, engineers improvise. We cram conversation history into context windows until we hit token limits. We build RAG pipelines that retrieve chunks of information and hope the right ones surface. We serialize agent state to databases between workflow steps. Each of these approaches works until it doesn't, and when it breaks, the failure looks deceptively like the model being dumb or confused. When a model hallucinates, most engineers blame the model, but a more disciplined diagnosis asks, what was actually in the context window when this happened? Stale information, contradictory memories, or simply missing context can make even the best model produce confidently wrong answers. When an agent loops forever, the question isn't why the model is confused, it's why your state tracking failed to record what the agent already attempted. The model is reasoning correctly given what it sees. You gave it the wrong thing to see. In traditional software architecture, your application manages state and your functions are largely stateless, a clean, well-understood model we've refined for decades. AI systems invert this entirely. The model handles the reasoning but carries no memory forward. That means you, the engineer, must make every consequential decision about state: what exists, where it lives, how it gets fetched, when it expires, and what happens when it's corrupted or out of date. This is a genuinely novel design discipline, and almost no tutorial series treats it with the seriousness it deserves. The teams shipping reliable AI systems in production aren't winning because of exotic prompting techniques or proprietary model access. They're winning because they got serious early about asking unglamorous questions. What exactly does this agent need to remember? For how long should that memory persist? A session, a day, forever? What happens when a user's stored context becomes stale or factually wrong? What's the recovery path when memory is corrupted mid-workflow? These questions feel boring compared to model benchmarks, but they are the actual architecture of a system that works reliably at scale. If your multi-step AI workflow is behaving unpredictably, apply a disciplined triage order. Start by auditing your state design. What was the agent's full context at the moment of failure, and was anything missing, outdated, or contradictory? Then examine your retrieval logic. Did the right memories actually get fetched at the right time? Only after ruling out state issues should you investigate prompt wording, and only as a last resort should you consider swapping models. Most production bugs never make it past step 1. The model was fine all along. The competitive edge in AI engineering has shifted. Early movers won by crafting clever prompts and picking the right models. The next generation of reliable, production-grade AI systems will be built by engineers who deeply understand state as a first-class architectural concern, not an afterthought bolted on after the demos look good. Before your next sprint, ask yourself, do you have an explicit, documented design for what your agents remember, how long they remember it, and what happens when that memory goes wrong? If not, that's where to start, not the leaderboard.